Day 93 is section 9.1, day 1. We'll spend 2 days on sequences. Some basic definitions. A sequence is a list of ordered numbers. If you take a formula and plug in the numbers n equals 1, n equals 2, and n equals 3, you get a list of numbers. This is called an alternating sequence because this part here, -1 raised to the n, will flip-flop back and forth between negative, positive, negative, positive. A picture of this sequence is over here. The input number n is the x-axis, the output number a sub n is the y-axis, and you can see it alternates because it flip-flops back and forth between positive and negative numbers. And as n increases, it would appear that this sequence also increases. Second type of sequence is a recursively defined sequence where the next term is based on previous terms. So you need to be given a starting point, sometimes one, sometimes more initial values, and then you build subsequent values off that initial value. So if A1 is 3, then A2 can be calculated by plugging in 1 for n. A sub 2 means n is 1, so I'm going to plug in 1 here, 1 there, and then I'm going to use a sub 1, which we were given in the previous case. So when I take 1 over 2 times the previous term, 3, I get 3 over 2. To figure out A3, if the subscript is 3, that means n is 2. I'm going to plug in 2 and 2 to get 2/3 is my fraction times the previous one. 2/3 times 3/2 is 1, etc., etc. A plot of this recursively defined sequence looks like this, and it looks like this one is always decreasing, and it also looks like it might have a finite limit. The first sequence oscillates back and forth and goes out to infinity. The second sequence, it looks like, converges to a certain number. So a quick review of some properties. Since sequences are going to be involving limits, some addition, subtraction, multiplication, division, and constant rules for limits are written right here. Basically, it says if you need to add two limits, go ahead and add the two results. If you want to multiply, if you need the limit of a product, you can just take the two limits and multiply them. Same with division, and a constant can be moved out front. So the limit of a constant times the sequence a sub n, constant moves out front. If the limit of the sequence is L, then it's just constant times L. Sequences often involve factorials or review of factorials. 16 factorial means you're going to go 16 times 15 times 14 all the way down to 1. So when I divide that by 14 factorial, lots of stuff cancels. The 14s, the 13s, all the way down to 1s cancel, and you're left with 16 times 15, which is 24. For a more abstract case where we're involving variables, n plus 1 factorial is n plus 1 times n minus 1 all the way down to 321, and then the denominator starts at n minus 1 and goes all the way down to 321. N minus 1 and down cancels, and you're left with n plus 1 times n, or n squared plus n. And then finally, another property of factorials, these grow faster than any exponentials. So n factorial is a function that increases very quickly. So to figure out whether a sequence converges to a single number or diverges, we're going to use limits. Here's my sequence definition. The limit of that sequence, the limit of 1 plus 1 over n, as n approaches infinity, this term disappears, I'm left with 1. This sequence converges to 1. Second case, when I take the limit of 2 plus -1 to the n, this value here oscillates back and forth between +1 and -1. So my overall sequence is going to be either 3 or 1. It's going to oscillate back and forth between 3 and 1. So this limit does not exist because it oscillates, therefore that sequence diverges. And then finally, in the last case, we have a sub n is 5 times n over e to the 2n. When I go to take the limit, I wind up with infinity over infinity. We learned in last chapter that that's an indeterminate form. So we tackle that by using L'Hopital's rule. Take the derivative of the top and the bottom. I get 5 over 2 times e to the 2n. Now that limit is 5 over infinity, which is 0, so this sequence converges to 0. And the last slide involves a special case. When you're dealing with trig, oftentimes the squeeze limit is very helpful. So if I have a sequence defined as cosine squared n over 3 to the n, I can look at cosine squared and say, well, that has to be between 0 and 1. Cosine oscillates between -1 and +1, and when you square it, it becomes only positive, so between 0 and +1. I'm going to take all three of these and divide by 3 to the n. I'm going to take the limit of the left, which is 0. I'm going to take the limit of the right, which is 0. So since the limit on the left and right bounds of this function, of this sequence here, is 0, that means that it must also be 0. The limit of the sequence must also be 0 by the squeeze theorem. So we know that a sub n converges to 0. So the squeeze theorem says that if you have a sequence that's between two other known sequences, and if you know that those two other known sequences have some sort of a limit that exists, then the limit for that unknown middle sequence also equals that same value. All right, that's it for day 1. The next slide says day 1, but that's actually part of day 2, so you can stop here and complete the day 1 homework.